Woo, welcome back. Tonight we're going to be working in 2.4, the average rate of change of a function. Yay! And I've invited my friend the sparkly vampire to join us because average rate of change starts with a fraction. Yay! So we're going to start off right with a bang. We're going to go right into a word problem, everyone's favorite. On average, babies in the United States are 20 inches long when they're born. By the time they're grown, men in the United States are 5 foot 10 inches tall on average by the time they're 20, when most are fully grown. From the ages of 20 to 30, men in the United States tend to stay the same height. So the question is, with all of that information, what is the average rate of change in height for a man in the United States over the first 30 years of his life? Okay, so here we're going to start off with the first thing you should be asking is, what the heck is an average rate of change? So, average rate of change is equal to, and then here the book, different books have different words. You either want the total change, or this book calls it the net change, over the time. So, in a problem like this, what you want to do is you want to identify what are you measuring that is changing. And in this case, if we read through the problem, we see that it is height. And I know it's weird to talk about the height of a baby. We usually say that they're 20 inches long because they're generally not standing when they're born. But, you never know. And then the timing, it seems like we're measuring things if we're saying 20 to 30 or the first 30 years. So we're looking for years. So I'm looking for years in terms of the time. And then the total change or the net change, this is a little bit more complicated because we're starting off that babies are 20 inches long on average. And then we're talking about a grown person being 5 foot 10 inches. So this is a mixture of units. And since the babies are 20 inches and the adults are 5 foot 10 inches, my tendency would be to go ahead and do this in inches, since we aren't told which we're supposed to look for. Sometimes problems will specify you have to do it in feet per year or in inches per year. So this one, we just got lucky. It's not asking us for anything specific. So my total change or my net change is going to be the final amount or the later amount minus the initial amount. So in this case, the initial amount is 20 inches. So that's pretty easy to start with, right? So we've got this 20 inches long. That's going to be our initial amount. Now, if I want to figure out the 5 foot 10 as the final amount, because we're told that by the time they're 20, it's 5 foot 10, and then generally there isn't a lot of change. So the final amount is going to be 5 foot 10. 5 foot 10 inches. Oop, let me scooch down so you can see that. Is equal to 5 times 12 plus 10, which is 60 plus 10, which I think is 70 inches. I believe that's correct. Okay, so the final amount is 70 inches. So this is nice. These are nice round numbers. I love it. 70 minus 20 is 50 inches. Now the time, well, the time is the average rate of change in height for a man in the United States over the first 30 years of his life would be 0 to 30, which is a total of 30 years. So the average rate of change, I don't know if anyone else writes AROC, but it seems pretty cool. AROC is going to be the 50 inches, that's the net change, over the 30 years, which I can reduce, and I get down to 5/3 of an inch per year. Or, and here I can grab my calculator, because this is a word problem, and a lot of times word problems we want to have written in decimals instead of fractions. So 5 divided by 3, it would be about 1.67 inches per year. Woohoo. Okay, so that is the average rate of change. So that means over the first 30 years, you could expect about 1.5 inches. And now it asks about the same problem. It says, okay, find the average rate of change in height for a man in the United States over the first 20 years of his life. Okay, so average rate of change is going to be the total slash net change over time. Now this time, see what I did there? This time. So this time, this is only 20 years of his life. Now let's take a look at the problem. That's going to be our time. If we look at the problem, we see by the time they're 20, they're already 5'10". So that means that the total or net change, that hasn't changed. That's still the 50 inches we got in the first part of the problem. But the time is now 20 years. Okay, so that's going to be 5/2 inches per year, which is 2.5, I believe. 2.5 inches per year. And now the question becomes, which one is correct? 1.67 or 2.5? Same statistics, but we're getting two different amounts. Are you growing 2.5 inches a year or only 1.5 inches a year? So, what's going on? And the important question that I want to answer is, what do they obscure? Number one, the answer in number one, ignores that there's no change in height for the age range from 20 to 30 years. So in other words, this is a case where you have to be very careful, because the average rate of change of a function can be misleading. The denominator, whether it's 30 years or 20 years, is really important, especially if you have a situation where, if we look at the graph, and I put time here, and I put inches here, what we have, and I don't know what it actually looks like, but I'm going to just suggest, if this is 20 and this is 30, I'm just going to give you a little bit of a graph. What's going to happen is we're going to do some, I don't know what the graph looks like, and then it flattens out from 20 to 30. So when you look at the difference between these two possible graphs. The first one gets up to this height, this 70 inches, or sorry, yes, 70 inches. And in fact, I have this is, oh my goodness, I dislike that I did this. You guys caught what I did. I see what I did. That was, what did I do? And right at this moment, I have run out of whiteout. That is terrible. Remember, we don't start at 0. We're born around 20 inches. So, in fact, it looks a little bit like this. Sorry about this. There we go. Much better graph. Thank you for your patience there. So, great opportunity to remind everyone that you can make mistakes regardless of how comfortable you are with the material. They just happen. So, thank goodness I got my mistake out of the way for tonight, though, right? So, here we can see that if we look just from 0 to 20, that we graph a steeper looking function. And if we look at the graph from 0 to 30, it's slightly less steep, right? This is a steeper one. This is the 2.5 inches per year. It increases much faster, and then it kind of stalls out. And this one, the assumption was that we're evening it out the whole way. So what is misleading about this problem? Well, this first problem is misleading because it suggests that it was the same change over every year, and that's the problem with averages. Averages literally take our information and spreads it out evenly. And anyone who's been human for any amount of time probably remembers that when you're little, you grow really fast. So this isn't even correct. You don't grow at a constant rate. You grow really fast when you're little, and then there's another growth spurt right in your teens where suddenly you grow a bunch, and then you just kind of stop. So there are a bunch of plateaus in there that we aren't representing, and that's the downside to looking at an average. So as we embark in 2.4, we need to make sure we really look at the information very carefully so that we don't let these numbers obscure what's actually happening. Okay, so that's the big warning at the beginning. And let's go ahead. Let me try one more problem. So this is not a word problem. This is more of just a straight up math problem. For f of x equals x plus x to the fourth. Okay, so we get a formula, which is really nice because we can graph it. We can look at what it looks like. It's awesome. And what we want to look at is the net change and then the average rate of change of the function. So the two different things that we're going to look at. Okay, so net change. To find the net change, what we do is we plug in x equals -1. So I've got f of -1 equals -1 plus -1 to the fourth. And that's going to be -1 plus -1 to the fourth is 1. And that's, 0. And then at x equals 3, so f of 3, again, 3 plus 3 to the fourth, which is 3 plus, I happen to know that this is 81, but you can always use your calculator. Keep it close by for this section. And so I get 84. And so the net change is going to be f of 3 minus f of -1. And immediately I can hear everyone saying, how do we know which one goes first? How do we know? And generally what I'm looking at is that x equals -1 comes first on a number line. It's the smaller number. And then we go to x equals 3. The other indication is it says between x equals -1 and x equals 3. So I'm going to read the graph from left to right. So I'm going to subtract the f of -1, which will be my original, my first, and subtract that from the end point there. So let's see, I get 84 minus 0, which is just 84. So that's my net change from -1 to 3. See how we reversed it? Okay. The average rate of change is going to look like this. So the average rate of change, remember, that's going to be the net change, or in some books it's the total change, over, in this case, normally this would be time, but we're going to look at, this is going to be the net change in y, or the output. And down here, it's going to be the net change in x. So here, because we're not dealing with a word problem, the average rate of change is just going to be the change in y over the change in x. Now, we've seen this. If I say change in y over change in x, basically we're looking at that's going to be our slope. So all we're doing is finding a slope, but we are finding it for something that is not a line. This is not linear. This is something that has a swoop-de-doop up like this. And so this is actually going to be something that we couldn't calculate a slope of, but we can look at something very similar. So how does this one look? Well, we've got up top, we've got the 84 minus the 0. And down on the bottom, I've got 3 minus a -1. So this is 84 all over 3 plus 1, just 84 over 4, which is just 21. Woohoo? Woohoo. Hopefully this one's a little bit faster because it's not a word problem. It's just the math. We're just interested in how much y is changing over the change in x. Woohoo? Okay. So I'm going to stop the video there, but I've got a couple more examples I want to talk about because I think this is a really cool and interesting topic. So let's go ahead and I will end the video. You guys are going to take a break, go get a nice snack, go get a nice nap if you need one, dance around, do some art, play some video games, whatever it is you do to chill out, and then come back and I'll have a second video with 2 more examples. Woohoo! Okay, math on.